Okay, moving on to day 2 for lesson 4. Some more about conditional probability, which we talked a little bit about yesterday. Okay, so we're rolling 2 number cubes for our warm-up. They have given us both the sample space and the associated two-way table. And the two-way table contains the sums of the 2 rolls. Last week in our notes, we generated this two-way table, and then from the two-way table, we generated a frequency table. So you've seen this table before. Actually, you had to make it last time. This time it's provided for you. So a little bit of a review here. The number of possible outcomes in this sample space is 36. We can count the outcomes in the sample space. We can use the fundamental counting principle here to say we have 6 possibilities on the first row and 6 possibilities on the second row, giving us a total of 36 possible outcomes. Now they've taken the information from the two-way table and put it into a frequency table. This frequency tells us the number of times this sum can occur or does occur in our sample space. The sum of all frequencies is 36. This number is also the total number of possible outcomes. The probability called using the frequencies from the frequency table are theoretical probabilities because they are calculated using known outcomes. If we were to construct a probability model for the sums here of the faces of the 2 number cubes, we would have a non-uniform probability model. So you can see right here, we've got 1 out of 36 for rolling the sum of a 2, and then I have 6 out of 36 for rolling the sum of a 7. While there are some probabilities that are equivalent in this model, they are not all equal, so it is non-uniform. Okay, got a bunch of parts to this problem number 1. We'll get you started on this and then let you continue on. The two-way table, same one we had on the front page, is below. And the total number of outcomes is still 36. And now we're going to be talking about the event of rolling a 5 first. And then B is going to be rolling a 4 or less on the second roll. These 2 events are independent. We are going to circle the outcomes that relate to event A. That's rolling a 5 on the first roll. So we go first roll, roll a 5. We will circle these possible outcomes. The number of outcomes is 1, 2, 3, 4, 5, 6. So the calculating the probability of rolling a 5 first would be 6 out of 36 possible outcomes, or 1/6. And that makes sense because 5 is 1 out of the 6 numbers on the number cube faces. Okay, now we're going to box the number of outcomes related to, this should say event B, sorry about that, rolling a 4 or less on the second roll. Now we go to 4, and we can get a 4 and we can get something less. So second roll, 4 or less. So we put a box around all of those outcomes. The number of these outcomes would be 1, 2, 3, 4, 5, 6 by 1, 2, 3, 4. So that's 24 outcomes for rolling a 4 or less on the second roll. Now we need to calculate the probability. We take our total number of outcomes, 36, and the outcomes associated with our event and make a probability ratio. 12 goes into 24 twice. 12 goes into 36 3 times. So I have a 2 out of 3 chance of that happening. Now we need to identify the outcomes for rolling 5 on the first roll and a 4 or less on the second roll. This "and" means it's happening simultaneously. This would be the number of outcomes that are both boxed and circled. So that's box and circle, box and circle, box and circle, box and circle. So there are 1, 2, 3, 4 outcomes that fit this definition. So we're going to use that number of outcomes over our total number of outcomes, 36. 4 goes into 4 once. 4 goes into 36 9 times. So I have a 1 out of 9 chance for both of those things happening. Now we're going to calculate the probability of rolling a 5 on the first roll and 4 or second or less on the second roll by taking the product. This is what we did yesterday. So we're going to take the probability of rolling 5 first, 1 out of 6, times the probability of rolling a 4 second, which would be 2 out of 3, and this is going to give us the same 1 out of 9. This probability should match the probability in box C because these events are independent. We know to calculate the "and," the intersection of two events, we can take, when they're independent, the probability of A times the probability of B. So if we just practice this, look at our example here. We need the probability of getting a job this summer is 0.23. The probability of getting a car this summer is 0.09. So the probability of getting a job and a car this summer is those two probabilities multiplied together. So you go ahead and you try this one here. Okay, conditional probability. We talked a little bit about this yesterday. This would be dependent events. So in the final part of problem 1 from the previous page, that's really an example of conditional probability, where we had those that were boxed and circled. The probability of rolling a 5 first and 4 or less second can be restated as the probability of rolling 4 or less, comma, given a 5 is rolled first. We would write the conditional probability as P, parentheses, 4 or less, bar, which means given, we rolled a 5. So let's go back to our table and examine how we calculate this conditional probability. We want to highlight only the outcomes that are associated with rolling a 5 or less. And tools up here, my highlighter. So I go to 5. These are all the outcomes that are associated with rolling a 5 first. And if I look and I count just the number of outcomes in this conditional sample space, because this is now my condition. This is the given part. I count, I have 1, 2, 3, 4, 5, 6. So now I'm looking in this limited or reduced conditional space on which I'm going to be calculating probabilities. Now we're going to circle the outcomes for rolling a 4 or less on the second roll, but only those that are in this conditional sample space. So I find 4 or less, and I circle the 9, the 8, the 7, and the 6. So these numbers of outcomes, if I count them, there are 4 of them. So now I'm going to create the probability ratio, but it's different now. We've been using 36. We've been using the total number of outcomes for the entire sample space for all probabilities up until this point. But now that I have a condition, because I'm calculating conditional probability, I am using this conditional or reduced sample space for my total number of outcomes. So the denominator here is going to be 6, not 36. My numerator is 4, and I get 2/3. If we go back to the previous page, to box B, we notice we got the same 2/3. Looking at it as the whole entire sample space. Now the reason that this happens, the conditional probability for 4 or less given a roll of 5, and just the probability of rolling a 4 or less on the second roll here are equal. This will not happen every time, and this happens because we have independent events. All right, so we're going to do continue on with problem 1. We're going to look at another part of problem 1 here. We're going to roll a 5 on the first roll, so this did not change. However, event B is now rolling a sum, not just a particular number, but the total of the two numbers rolled that is greater than or equal to 8. Here, event A and event B are not independent, but dependent. The sum that we get from the roll of the two number cubes depends on which numbers rolled. We saw we didn't have that uniform distribution. We had way more chances to add up to a number 7 than we do to add up to any other total. For example, if we roll a 5 first and a 1 second, it is not possible to get a sum of 8 because 5 plus 1 equals 6, not 8. The condition of rolling a 5 first is not sufficient to guarantee the sum of it and the second roll will be 8. However, rolling a 5 first and rolling a 5 second does produce a sum greater than or equal to 8. So our first part of problem 1, we had independent events. Here in the second part, we have dependent events. You're going to start this problem the same way you started the other one. We are going to first highlight the number of outcomes for the given. This is our condition. And so we notice that the total number of outcomes for rolling a 5 first is 6. This did not change from the previous scenario because we didn't change the condition. So this is 6 out of my entire 36 or 1 out of 6. Now we're going to box the outcomes for a sum greater than or equal to 8. So here I'm not looking up here to get my information. I'm looking inside the table for the sums. This is 8 and larger, 8 and larger, 8 and larger, 8 and larger, 8 and larger. So I have this staircase shaped figure now. And if I count the number of outcomes that are equivalent to 8 or larger, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So the probability here of a sum being greater than or equal to 8 is 15 outcomes out of, again, our total 36. The outcomes of rolling a 5 first and a sum greater than or equal to 8 are those that are both highlighted and boxed. So we have 1, 2, 3, 4. Oops, 1, 2, 3, 4 of those outcomes. Okay, where were we? Okay, so the outcomes for rolling a 5 first and a sum greater than or equal to 8 are those that are both highlighted and boxed. So that's these 1, 2, 3, 4 outcomes. And that's 4 out of the 36, or 1 out of 9. Oops. Now, like we did before, we want to multiply the probability of rolling a 5 first, which was my 1/6, and the probability of getting a sum greater than 8. I guess I can reduce that. 3 goes in there 5 times, 3 goes in there 12 times. So that would be 5 over 12. So this is going to be 5/72. Okay, we are now looking at how the intersection here, this and the two multiplied together, they do not equal each other. So this total, 5/72, does not equal this probability of rolling a 5 first and a sum greater than or equal to 8 because the events are not independent but dependent. So this idea of independent and dependent is huge for how we are going to calculate probabilities. Now we're going to go back to our highlighted outcomes related to rolling a 5 first. We are going to circle the outcomes in this conditional sample space that have a sum greater than or equal to 8. The number of outcomes circled is 4. Now we're going to calculate the conditional probability of rolling a sum greater than or equal to 8 given 5 is rolled first. This, because it is a conditional probability, we are using the reduced sample space, the 6 outcomes that are associated with our condition. And then in that condition, the 4 outcomes that meet the criteria, and we get 2 out of 3 opportunities. Now, if we look at this 2/3 and the sum, just rolling a sum greater than or equal to 8, which is 5 out of 12, again, these two are not equal. They were equal in the previous example. They're not equal here because the events are dependent. All right, we have provided you with the correct data. Now you need to collect that data and follow this chart. See how the formula is developed and apply that formula. And then we want you to go ahead and try this SOX problem. So you need to kind of get this done first. So you're collecting the data from the part 1 and part 2 of the problem, putting that in the chart, doing what you're told, and analyzing what's happening, reading, and then applying that formula. Okay, and just real quickly to get you started on problem 2, you have 2 red socks, 1 blue sock, and 1 yellow sock in a drawer. You reach in without looking and choose a sock without replacing it and then choosing another sock. So we did this yesterday with changing the probabilities to get what the intersection would be. Today we're going to be looking at it as conditional probability. And then go ahead and check with your partner, your information. We need you to kind of explain the difference between these two probabilities and then complete your exit slip.